Hi everyone. In the previous video, I provided a formula that can be used for finding the average value of a function. And in this video, I'm going to explain where that formula comes from. We're going to see this is also going to provide a good opportunity to review various concepts relating to integrals that we're going to need throughout the rest of the course. So here's the formula for f_av, which I gave you before. And just to remind you, f_av can be thought of as the average y value, or in other words, the average height of all the points on the curve. And that could be visualized by this blue line. Now, let's provide a proof of why this formula is correct. The real difficulty with calculating the average value of a function is that there are infinitely many points that need to contribute to our average, but we can't add infinitely many things together. The next best thing would be at least to try to get an approximation of the average, right? Although we can't possibly account for every single point on the curve, we could still get a pretty good estimation of f_av if we were to select a whole bunch of points on this curve and average out their y values, with the understanding that a larger number of points would provide us with a better estimation of the average. For example, if we were to use 1 trillion points in our average, we would get a much better estimation of f_av compared to if we only used 2 points in our average. So for the purpose of estimating the average, let's grab a few points on this curve. The first point I choose is what I'm going to call x1. I can grab another point and call that x2. Likewise, my third point can be called x3. And I'm just going to keep doing this to get x4, x5, and so on, until eventually I grab the last point for my average, which I'm going to call xn. Now notice that by naming this last point xn, there's an implication that n represents the number of points which will contribute to our average. And in doing this, I've avoided specifying exactly how many points that's going to be, but there should be an understanding that our estimation is going to be better if n is a large number, since that would indicate that a larger number of points are being used in our estimation. Now that we've selected all these points, we can start building a formula which would at least give us the approximate value of f_av. Now remember that f_av represents the average of the y values, so we would need to add together the y values of all these points. The y value of our first point would be f of x1, since we know the y value is obtained by plugging in the x value into our function. We would then have to add the y value of our second point, which is f of x2, and we would continue adding all these values together, as I've indicated by ... And eventually, we would add the y value of our last point, which we can call f of xn. When forming the average, we also need to divide by the total number of things which were added, which in this case is n. So this is a good start. We don't yet have a formula for what f_av is exactly equal to, but we do have a formula for what it's approximately equal to. Now, in order to go from approximation to true equality, we need to find ways to ensure that our estimation is as accurate as possible, ideally with the goal of making it exactly accurate. So here I've just copied down the results we've obtained so far, although you'll notice I pulled out the factor of 1 over n in front of the formula for reasons that will become more clear in just a moment. I've just pointed out that we need to find ways to make our estimation as accurate as possible, and one way to do that would be to ensure that all the points we use in our average are equally spaced apart. Because after all, if all the points in our average were crunched together in one place, we wouldn't get a very good picture of what's going on with the entire curve. So let's give the space between each of these points a name. I'm going to call it delta x, as you see here. And that's a pretty common notation which is used to denote a change in x, so hopefully that notation is reasonably familiar to you. But let's think about what delta x should be equal to if we really want this even spacing of points. If I were to take the length of the entire interval and then divide it by the number of points, that would tell us how far apart each of these points should be if we really do want them equally spaced apart. Now it's pretty easy to see that b minus a would represent the length of the entire interval, since that's just the difference of the x-coordinates that define the interval. And as we know, the number of points is what we called n. So this formula, b minus a over n, represents the distance between each of the points that we're using in our average. Now, if we look back to the formula for f_av, we'll notice this factor of 1 over n is something that also appears in our formula for delta x. In fact, we could rearrange the formula for delta x to make a statement about what 1 over n must be equal to in order to account for this equal spacing. So a bit of basic algebra will reveal that 1 over n is equal to delta x over b minus a. Right, to come up with that, all I had to do was divide both sides by b minus a. What I'm going to do now is substitute this expression for 1 over n into my formula for f_av. And in doing that, the formula itself contains this information which will improve the accuracy of our estimation. And so our formula for f_av now looks like this. You might notice this formula we've come up with is starting to look a bit like the one I gave you in the previous video, at least in that it has the 1 over b minus a in front. Well, actually it has delta x over b minus a, but this could become 1 over b minus a if we distributed this delta x into the brackets, as I've just shown here. So let's go ahead and do that. Multiplying delta x to the first term, we get f of x1 times delta x. The second term would be f of x2 times delta x, and similarly for the rest of these terms. Now let's examine each of these terms in the brackets, starting with this first one. If we think about what's going on graphically, we know that f of x1 can be thought of as this vertical distance between our first point and the x-axis. And delta x can be thought of as this horizontal distance between each of our points. That means that f of x1 times delta x can literally be thought of as base times height, or in other words, the area of this rectangle. In similar spirit, if we look at this second term, f of x2 can be thought of as this vertical distance, whereas delta x can be thought of as this horizontal distance. So once again, we see that f of x2 times delta x represents base times height, so that is the area of another rectangle. If you were to go through all these other terms, you would observe something very similar for those ones as well. And so it's fair to say that each of the terms being added together here represents the area of a rectangle. In fact, what we're seeing here is an example of a Riemann sum, which is a way to approximate the area under the curve by adding together the areas of rectangles. That is a concept that you should be familiar with from your first calculus course. Now, another way that we can improve the accuracy of our estimation is by incorporating more and more of these points into our average. Right, because we'd get a better estimation if we took the average of 2 million points than if we took the average of, say, 200 points. So in other words, our estimation would be as accurate as possible if we were to let n approach infinity, since n represents the number of points. So if we take this limit as n goes to infinity, we should end up with the exact value of f_av rather than just an approximation, and that is what we want. Now let's think about this graphically. If we let n go to infinity, that means we're crunching more and more of these points into our interval, so the distance between each of those points would have to become smaller and smaller. That would have the effect of making each of these rectangles thinner and thinner to the point that you might call them infinitesimally thin. And that's just a fancy way of saying that they're thinner than any object which you could possibly even imagine. And if our rectangles are infinitesimally thin, then adding together their areas will provide us with the exact value of the area under our curve, as you might remember from learning about Riemann sums in your first calculus course. Another thing you should remember is that the area under the curve is what we call the definite integral, or in other words, the integral from a to b of our function. So putting this all together, we can take that entire expression which I circled and call it the integral from a to b, since that carries exactly the same meaning, and in doing that, we have confirmation that the formula I gave you for f_av is indeed correct. That's what we set out to do in this video, so I'll wrap things up here and I'll see you next time.